Welcome to this class on the principle of stratigraphy. We will try to understand the meaning, principles and the meaning of the word stratigraphy. Stratigraphy is a study of layered rocks, and mostly the sedimentary rocks are layered. So, most of the effort made in stratigraphy is to deal with the sedimentary rocks. We also have layered igneous and layered metamorphic rocks, and that also is included in the stratigraphic discussions. What is exactly studied in stratigraphy? Two things: the age becomes very important and the correlation. We try to understand each of these words. Age in stratigraphy can be of two types: the relative age and the absolute age. What is the meaning of the word relative age? If I say rock A is older than rock B, or if I say rock A and rock B are of same age, so many millions of years or so many billions of years. This means we are using the concept of relative age. We are not specifying the exact age of A or the exact age of B. Such conclusions or interpretations have a very far-reaching implication in stratigraphy and in applied geoscience. And what is the meaning of absolute age? Here, suppose I say rock A was formed 3.2 billion years ago. If I say that rock A formed 3.2 billion years ago, then in this statement we are putting the exact age of the rock. So, this 3.2 is the absolute age. GA stands for billion years or giga annum, and it can also be written as BA, short form of billion years. MYA and BYA can also be seen in stratigraphic literature. MYA means millions of years ago and BYA means billions of years ago. The word annum, which is used, is a Latin word which means year. This absolute age of the rock, such as 3.2 billion year, can be obtained by radiometric dating, and in this NPTEL lecture we will cover in detail the chronostratigraphy, where the different dating techniques will be explained. For our information, the age of the earth is 4.6 billion years, which is same as 4600 million year, or we can write it as 460 crore years. And the age of universe is 3 times the age of the earth, so 3 multiplied by 4.6 billion years. We are not getting into the age of universe and age of earth, how they were derived right now. Now from here we go back to the second issue in stratigraphy that is worked out, is the correlation of rock units. Let us try to understand it. Suppose these are the two depressions in the past, and from elevated area sediments came and got deposited. Rock unit A, B and C is found in one basin, and in another basin we can call it basin 1, this as basin 2. Within basin 2, units A, B and C also got deposited. Through the word correlation we mean, if the unit A here and that unit A here deposited in the same age, then from the lithological logs keeping side by side we can put dash line and we imply this A unit correlates with this A unit. Similarly, the B unit correlates with the B unit, and the C unit at the topmost layer correlates with unit C. Now, this is for the beginners presentation, and in this NPTEL lecture I will be talking about different correlation techniques used in stratigraphy, and you will eventually see that this diagram is super simplification. The actual correlation is much more complicated than this. Another point, in two basins, basin 1 and basin 2, even if we get rock A, B and C, and in another place rock A, B and C, there is no guarantee that this A and this A were deposited simultaneously. Sandstone is found of different ages in the earth record, not all of them are correlated in this way. Another point, remember that the same rock type can be layered or non-layered, both are possible, and the easiest example can be sandstone. We can have sandstone with many bedding planes or layers, or we can also have massive sandstones. Another point, when we were correlating ABC from basin 1 into ABC of basin 2, it is not guaranteed that this basement and this basement were of same height. It may not be of the same height. So, height from the mean sea level MSL can differ for these two basins B1 and B2. That means this height from the mean sea level and this height from the mean sea level may or may not be the same. So, instead of drawing the lithologs side by side in this way, one can also draw the lithologs in this way and say that this is a very common way of presentation. Unit A are correlated, then unit B is correlated, and then unit C is also correlated. Note that in the two different basins, even if the same rock is depositing, even if the same sediment is depositing and eventually becoming a rock, their thicknesses may differ. So, there is no guarantee that the thickness, the highest thickness A here and the highest thickness A here will be the same. Nevertheless, they can be of same ages. So, they can be correlated. Now, let us see what did we mean by the word principle. There are common principles or common theories involved in finding the age of the sedimentary rock worldwide or correlation of sedimentary rock from one place to another. Those are known as the principles. So, attached with the word stratigraphy, you can find principles of stratigraphy, which is the topic of this NPTEL presentation, or you can find country specific description of stratigraphy. So, you can find a book on Indian stratigraphy, you may find a book on German stratigraphy, or there can be terrain specific discussion of stratigraphy. So, if someone says the Vindhyan stratigraphy, that means of the Vindhyan supergroup, the stratigraphy has been explained. So, if you visit library, you will find there are books like Principles of Stratigraphy, and you will also find say Indian stratigraphy or say Nordic stratigraphy. If one wants to see a book with great detail of a specific terrain or specific basin, let us say Vindhyan stratigraphy or the Gondwana stratigraphy. In this NPTEL lecture, we will look at the common principles, the science behind how to find the age, how to correlate the rock units. However, do not think that stratigraphy 100% deals with layered rock. There is also a way of dealing with the non-layered rocks, that also we will see. So, not just, so I can write study of mainly the layered rocks, and I can add up here also non-layered rocks are included. Now, let us see stratigraphic relationships amongst the layered rocks. Unconformity is one which I will be covering in a separate lecture series in detail. You can look at the lecture titles and you will find a full discussion on unconformity, and you can have a look after this discussion goes over. The principle of superposition, or it is also known as Steno's first law. Steno gave this simple law that units higher in the stratigraphic sequence are younger than the bottom unit. I will explain it. And Steno originally gave this concept for the depositions that happen within water. This means, suppose this is the basement over which water is bringing sediments and depositing. Suppose sediment P got deposited, then Q got deposited, and then R got deposited. The bottommost unit is the oldest, topmost unit is the youngest, and any unit which is at the top of another, such as Q is at the top of P. So, Q is younger than P, R is at the top of Q, So, R is younger than Q. So, altogether we can make a succession unit P, unit Q and unit R, O for old and Y for the younging direction and this arrow vertically up. As a consequence of Steno's first law, think of there is a hill and there is a nearby depression. If I am getting a succession A followed by B followed by C, that means in the hill that got eroded from where the sediments came, if at all we can establish, which is now an eroded hill, the layer which was at the bottommost has to be in the topmost position, because this is going to be eroded first, then layer B and then layer C. This is a simplified model. Now, there are certain exceptions of the Steno's first law. What if sedimentary deposits get overturned? Imagine due to some tectonic reason this PQR got folded in this way. This is a sketch of a recumbent fold, or we can call it a neutral fold. Here if you drill, you will find unit P, Q and R, and if you drill over here you will find R, Q and P. So, while this normal succession can be found over there, an exact overturn has happened in one of the limbs. So, if your observation is within the overturned limb, your interpretation can be completely wrong. Therefore, it is very important to decipher stratigraphy, look at structural geology of the terrain. Is the terrain faulted? Are the lithologies folded? The complete structural history also is to be understood. Then only we can find out a proper stratigraphic succession. I can make a statement here. Perform detailed structural geological study to decipher the succession. That means succession of how the lithology got deposited one after another. We have covered the overturned case. We will now take another case of overturn through the Rayleigh-Taylor instability. What is that? Imagine layer N got deposited first and then layer M got deposited, but the density of that layer M, rho M, is more than the density of the layer N, rho N. What will happen in this case? The highly dense material will try to go down over millions of years. Rock move in a ductile manner and M finally goes down, N moves up. So, after years this situation is possible, a complete overturning has happened. An easy way to understand this is to think that there is a tank and half of it is full of kerosene, and over that we are pouring water. Water being denser will move down and kerosene will float up. This happens rather quickly in the laboratory because of the strong density difference, whereas in the geological case the density difference can be low. Rho M and rho N, I can write delta rho can be as low as 0.04 gram per centimeter cube. If such is the case, then over years an overturn is possible. So, at present if we look at this, we may start thinking that this is the succession, as if M got deposited and over that is N. Now, this will be wrong, and the correct one will be, if complete interpretation is made, N got deposited first and M. So, the question comes, how do we know? If we find layer M and N in nature, how do we know what has happened? There are ways of doing, and for that one can look at the concept of diapirism, doming, etc. We will now take a case of seal intrusion and see that the principle of superposition, Steno's first law, will not work in this case. Consider there are sedimentary rocks A, B and C, and this is the basement. Suppose we establish no overturning has happened. A, B, C are the sedimentary rocks, here is the basement. If the layers are not overturned, then A is the oldest, B is the younger, then B got deposited younger than A, and C is the latest depositional product. Now imagine an igneous material K is intruded at the A B interface. If we are blindly doing the superposition principle, then we will interpret first A got deposited, then K came into existence, then B and then C, but this is wrong. What is correct is that a proper interpretation will be first A, then B, then C, and after that K came into existence. Through field work and possible geochronologic studies, finally to reach this succession. Let us take another case of alteration. Rock unit A, B, C got deposited, and in the later phase, due to fluid activity, a part of B got altered to L. So here the correct sequence will be A got deposited first, then B got deposited, then C got deposited, and then rock L came into existence. In Steno's first law, seal intrusion, alteration, the Rayleigh-Taylor instability and the overturning situation may not come based on where Steno was working to study, and he emphasized that he was dealing with water laid deposits. Now once I said an igneous intrusion K, it is not a water laid sedimentary deposit. So in that way Steno's view can still be justified. In the field one should try to see as much as possible, as many geological sections as possible. We can see rocks beneath our feet while doing field work. Suppose a road is constructed and for that blasting is made, or a river has cut across the rock, then we are finding the rocks as vertical sections. We can also see rocks in the inclined sections. All these sections to be studied, as much as possible should be looked, as much as possible areas should be covered in the geological field work to get a complete picture. Now we will see the cross-cut relationship. Suppose in the field we are observing either on a horizontal section or on vertical section or in an inclined section, we see that rock A has been cut by rock B. So here we say that rock A is older and B is younger. What can be the example of rock B? Dikes and veins. There are two spellings of dikes for the beginners, DYKE dike and DIKE. But in your research paper, in your thesis, use a single spelling. Dikes and veins commonly cut across rocks. What can be this dike material? Now they are mostly igneous melts, igneous rocks therefore, but there are also sedimentary dikes possible. An example of sedimentary dike can be sandstone dike. Suppose you can clearly see such a relationship in the field, one rock cutting another rock, and you pick up a sample from A and you pick up a sample from B, and you take them in the laboratory and you find that the age of A is less than the age of B. Over this age that is found by mass spectrometer by some specific dating technique and a simple field geological observation such as this, we will rely this observation, we will question this age. If you find a relationship A age is nearly equal to the same as B age, that also will be questionable. What is expected for such a cross-cut relationship is that A age should be more than B age. If we find this, that means our field observation and the mass spectrometer derived geochronological date are matching. Let us look at the principle of included fragments, and using this we find out the relative age. Using Steno's first law, by creating a lithological succession PQR, we only mean a relative age. Q is younger than P, R is younger than Q, R is younger than P, R is the youngest unit, P is the oldest unit. We do not bring the concept of age, absolute age in this case. Whereas, in case of a cross-cut relationship, if it is a field observation, same thing we will be meaning that one is older, another is younger, we do not know the absolute age. If we date them, some ages are obtained, these are the absolute ages. Once we talk about the included fragments, here we are bringing the relative age. The exact age, the absolute age of the rock is not understood. What is the statement for the included fragments? The fragment in a clastic rock must be made up of a rock that is older than the strata in which the fragments are found. Let us understand it in terms of a simple diagram. Imagine there is a rock Z, and within that, as inclusion I am finding a rock M. So, what does it mean? It means that rock M is an older rock and now it is completely surrounded by rock Z. Z is the younger rock. So, if we go for geochronological dating and if we find that the M age is more than Z age, that means our mass spectrometer is working properly. If we find M age is less than Z age, this will indicate that there was some mistake or some altered materials might have been dated. Note that here both Z and M have to be rocks, none of them are minerals. Within a rock there can be several minerals A, B, C and D. Here M is not a mineral within rock Z. M is a rock, Z is a rock. So, be careful while applying this principle. M must be a rock, it must not be a mineral, a piece of mineral. Now, in case of igneous rocks, say Z is an igneous rock, M can be called a xenolith. If Z is an igneous rock. Now, moving into the basic concepts of stratigraphy, let us look at Steno's second law. It is also known as the law of original horizontality. What it says? Sediments laid down by water, such as laid down in a river, in a lake, in shallow marine condition or in deep marine condition, these layers are always parallel to the depositional surface. What it means? This basement and this line can be called as a depositional surface over which water-led sediments are getting deposited. Unit A, unit B and unit C. We can see the contact between A and B, the contact between B and C, and these contacts are parallel to the depositional surface. I can call this as small t. Small t is the depositional surface. So, the AB contact is parallel to the small t, BC contact is also parallel to the small t. So, as a corollary we can say that these lithological contacts also are to be parallel to each other, which is coming from the Steno's second law. Note that in Steno's second law, it is nowhere said that the layers will be horizontal. Commonly we are thinking that the basement is horizontal or near horizontal and over which horizontal layers have been deposited. There are so many evidences that shows that the basement can be undulated. I have drawn here a case of a basement which is undulated. So, here is a depression. Now, suppose from outside sediments are coming, layer P will be deposited and followed by layer Q. We can see here that in this place or in this place the layers are not horizontal because the basement was undulated, and very strictly speaking in these portions the lithological contact Q and P, the lithological contact between Q and P is not parallel to the basement either. The basement here is a the depositional surface here is a curved surface. So, in one way this is a limitation of Steno's second law, and this is very common. We see such things in the seismic images. Let us come to Steno's third law, which is also said as law of original continuity. All water-led strata must continue laterally. That means, if this is a depositional surface and the water-led strata are there, I should find them continuous, but there is a limit. It is laterally, but not infinitely. Somewhere it has to terminate. So, the corollary of third law can be truncation of original sedimentary layer is there, and there can be two possibilities. By field work we can find that there is a faulting that has happened. Say there is layer P that got geologically faulted, half arrows indicate faulting, or there is a layer P and there is a natural erosional surface. So, there got a truncate. Where is the truncation here? This is the place where layer P is truncated, it does not continue in this direction. Here layer P is truncated, it does not continue in this direction. By natural erosion, this part is the end of layer P and it does not continue further. So, this is the meaning of truncation.